Raman, start position.
Thank you very much, Stefan, for the introduction. And thank you very much, Laurent, for giving me 20 minutes to explain Raman spectroscopy. But will be enough, I guess. Will be enough. So, because we have tight time, I will not start today with this fairy tale, naive history about Disney and so on. We will go straight to the real world with Marvel. And speaking about Spiderman, Batman, and Raman, and all the superpowers that we can have if we use Raman spectroscopy. Basically, I'm not the expert on Raman spectroscopy in my lab. Actually, the real experts are these two guys, Alejandro and Victor. And I am here just because it's cheaper for the organization. So, so if you really would like to learn about Raman spectroscopy, you must contact these two guys, that the real experts. So this is the outline of my talk. Even if it looks too long, too many points, will be quite fast, don't worry. And you need to know that most of the work that I am presenting are mainly being done by all these guys with the circle in red. Sorry. Right now you will recognize much better than me. Okay? So, what is the main motivation of using Raman spectroscopy in thin film photovoltaic technologies? Basically, as I presented yesterday, and also you learn from other technologies like silicon, perovskites, and so on, we have a lot of different layers in this structure. So the analysis of all these layers and understanding of all these layers and also interfaces is very relevant for improving our devices, but also in a production line, I will show you, for the control of this layer. And basically, with Raman spectroscopy, we can have access to some critical control parameters, like thickness, composition, secondary phases, and defects. And this is some explanation for the people working on silicon. Yes, there are materials with secondary phases and defects. Crazy people like me working with this kind of material. So for all these parameters, we can have a solution with Raman spectroscopy, as I will show you before. Then, basically, using our superpowers of Raman spectroscopy, we will have access to really characterize our solar cell device without destroying it. That is the most relevant point, probably, of Raman spectroscopy, because it's a purely optic technology. Then, in the general process of production of a solar cell, Raman spectroscopy can be used in different stages. It's very useful for different stages. You can see here the typical structure of a thin film solar cell, in that case of copper indium gallium diselenide, but can be catalurite or kesturite. And this is the P1, P2, P3 connection that I tried to explain yesterday. And then for producing one of these modules, you always start with the substrate. In that example, for example, glass. Then, this is probably the most hated process for the student in the lab, to wash very carefully this glass. And then you sputter the back contact, molybdenum in that case. You made the first scribing, the P1, this one here. Then you wash again to remove all possible powders and so on, and particles created during this scribing process. And you deposit your absorber, in that case, copper indium gallium diselenide, combining a sputtering and a reactive annealing. Then you deposit your buffer layer, in that case, cat sulfide. And you scribe again the P2, that is here. Finally, you deposit your window layers, like zinc oxide with zinc oxide doped with aluminum, or the window layer you are using. the third scribing process, the P3 process, that is here. And finally, encapsulation, front sheet, and so on to finish your module. And you measure it. If you are using just electrical measurement for characterizing your device, this means that you have to finish it. That is extremely expensive to know if your device is good or not. What Raman spectroscopy and another techniques allow is to start to characterize every single step in this process. And if some of these steps fail, you can stop the production of your module and then save a lot of money. And this is one of the main advantages. But of course, before having in hand this technology for the inline control and the quality control at industry level, you need a lot of laboratory research in order to develop all the methodologies and parameters that you can use for characterizing your process. Then what the industry want, of course they want always more for less, is all this. A non-destructive method provides physicochemical information compatible with large scale, compatible with inline monitoring, fast, cost-effective. So many, many things. And in most of the cases, Raman spectroscopy fit all of them, as I will show you afterward. Some definition of Raman spectroscopy. Basically, what we are using in Raman spectroscopy are all the photons that Laurent don't use or don't care or don't want. Basically, are all the photons that are not involved in photoluminescence we are using here in Raman spectroscopy. And basically, give information about the energy of the photon created and annihilated in the scattered medium. And this information is a fingerprint of the compound, so it's very important, so it can be used for recognize a compound or for identify a compound, and also contains a lot of information, including crystal structure and even composition. As examples, in copper indium diselenide, you have at least two types of structural polytypes, chalcopyrite and copper gold, as I briefly explained yesterday, and using Raman spectroscopy, you can really differentiate between them. And this is very relevant because this is the photovoltaic active absorber, and this is like wood or a stone. This is non-photovoltaic material. So you would like to avoid always the formation of this phase. And with Raman spectroscopy, you can have access to separate them and identify them separately. Also crystalline quality, you can really identify bad crystalline material or very good crystalline material with Raman spectroscopy. And even atomic composition, because Raman signal depends on the environment of your atom. So if you are looking at a vibration of a selenium-selenium bond, for example, depending on the environment of this selenium and selenium bond, you can have different signal. And this is a very clear example in our thin film chalcogenide technologies. You can see here the copper indium diselenide signal. This is the selenium-selenium vibration in copper indium diselenide, and this is the selenium-selenium vibration in copper gallium diselenide. So just changing indium by gallium in your lattice, you shift your Raman peak, and then you can have access to compositional information. Here you can see copper indium sulfide. If you change selenium by sulfur, of course the change is more drastic because this is a sulfur-sulfur vibration. Then the same, you can have access to composition, and the same for copper gallium disulfide. So all this information can be obtained with a simple Raman spectra that in somehow is very complementary to X-ray diffraction. So normally you use both techniques together because can together give a lot of information about the material. So, some really brief fundamentals about Raman scattering. So basically in the classical approach, what you have is an incident electrical field, that is your excitation light, that interact with the electrons clothed in your material and also with the nuclei that are oscillating, and then you have a modulated oscillating dipole moment. And of course, in that case, light is scattered. But you can scatter the light in two ways at least. The elastic scattering, where the light keeps the same frequency and the same energy than the incident light. So, and this light is mainly used, for example, for photoluminescence, or the non-elastic scattering. And you can have less energy through the phonon destruction or more energy through the phonon creation. And basically, this kind of inelastic scattered light is what we are using for Raman spectroscopy, because have a lot of information about your structure and your composition, as I told you before. And to give you an idea, for every 1 million of photon created elastically, just 1 photon is created non-elastically. So this is the complexity of the Raman spectroscopy, that we have to identify this signal among 1 million of photons that are created elastically. So it's for that that you need special optical setup, special laser for Raman spectroscopy. Same setup that is used for photoluminescence, most of the time is not useful for Raman. But nevertheless, if you have a Raman setup, you can use it for photoluminescence without problem. And also because this energy difference is very small. So this peak is 1 million times more intense than this, that is the Raman peak, but the difference could be 40 millielectron volt, 30 millielectron volts normally in common material, so it's nothing. Then the Raman spectrum fingerprint is characteristic for each material and basically depends on the crystal structure of the material, of course, in the atomic base, and also in the type of atoms you have in your structure. In the crystal structure, because each type of crystal structure has different symmetry, then have a specific family of vibration and different type of mode, A mode, B mode, E mode. For example, chalcopyrite have all these type of modes. Atomic base, because change the total number of modes. For example, in crystalline materials, we have 3n minus 6 mode, where n is the number of atoms in the unit lattice, and their distribution for each type of mode. For example, in a primitive cell of 5 atoms, then we will have, following this formula, 9 Raman modes. In an atom with, in a primitive cell with 8 atoms, we will have 18 different Raman modes. Sometimes some of them are silent or non-active, so this also depends on the symmetry of your structure and so on. It's relatively complex to explain. And finally, of course, the type of atom, because we are speaking about vibration, and it's not the same to move a light atom like sulfur or a heavy atom like tellurium, for example. And then this also, of course, gives a lot of information about the composition of your material. So basically, what the people apply normally in Raman spectroscopy is the group theory in order to estimate the number and type of mode expected for a compound. Normally describe this will require 2-3 hours to try to understand and go deeper in this theory. So I will not go deeper on that, and I am not the right person to really explain very well this. Then estimate the frequency of the mode required to apply simulation with a lot of approximation, and it's extremely complex as well. So normally you need really apply software for modeling in order to model Raman spectroscopy. It's not as easy to just recognize the number of modes. If you would like to estimate the frequency, you have to go toward the more complex softwares. Even if Raman looks like a very nice technique, and already is a very nice technique, there are some properties that could compromise really the characterization of semiconductors. First is a process that involves 3 particles, so at least 2 atoms that are vibrating and 1 phonon in between. And then need for high sensitivity detector, because this is a very weak interaction. As I explained you before, more or less 1 photon of every million of photons scattered correspond to inelastic or Raman scattering. So this is very, very few quantities of photons. This phonon energy is very low, so as I also told you before, it's around 40 millielectron volts, even less in some cases. So this makes the detection of Raman signal very difficult because it's very close to the elastic scattered light. So you have to recognize a very small peak together with a very intense peak, and this makes very complex Raman detection. So you need high power dispersion system and filters to reduce or eliminate as much as possible this scattered light or elastic scattered light. And finally, this inelastic scattering energy depends on the incident light. So if you change a bit your incident light, you can have impact in this inelastic scattering energy. Then you need high monochromatic and frequency stabilized laser, because if it's not monochromatic, you can have really shift in the peak, and then to filter this from the Rayleigh peak could be much more difficult, and very stable laser. So standard lasers are non-compatible with Raman, and we need specially stabilized lasers in frequency and with a very, very narrow emission line. So we need a special system for Raman setup if you would like to build one. It's used to be quite expensive, and this is the standard Raman setup. So with all these parts in order to acquire a very nice Raman signal. So what we need first is a monochromatic beam generated by a laser here that have a band pass filter here which eliminate parasite contribution like plasma line in gas laser or background in solid state laser. So this first optic thing here is basically to clean a bit your laser. Then the cleaned laser beam cross this beam splitter, and with this lens is basically focused in your sample in a second step. Then all these photons are scattered everywhere, and the small fraction of photons that are scattered then go through this lens once again, through the beam splitter again, and are directed toward this monochromator. Basically here in 5 you have once again an edge filter in order to clean a bit this signal, another lens to really focus this into your monochromator, and the light then enter to your monochromator. Then when the light enter to your monochromator into the spectrometer or monochromator through this slit, then is directed to this in the next step, here. In the next step, in a parabolic mirror, is directed toward a grating where the light is separated by wavelength, and then directed toward your detector. That you detect a different wavelength in order to have a Raman spectrum. So this is basically the setup. It's relatively similar than the PL setup, but you need really very high quality optical optical components and also a very good monochromators. Normally, for example, in IREC we build our Ramans, and normally we have triple monochromators in order to have high resolution Raman. So this means we don't have just one monochromator. We have 3 monochromators together. And then you have a really very high resolution. This type of single monochromator is for having very intense signal that can be very useful, for example, for the industry. Once you have your setup, not anything is perfect, because Raman spectroscopy in principle is a non-destructive technique, but this is true if you take into account some limits, because the intensity of the light that you can illuminate your sample can be really very big. If the irradiance of the sun is of the order of 0.1 watt by square centimeter. But if we take a laser beam of just 1 milliwatt, so it's a really very low intensity laser, and we focus it in one spot of 1 micron, then the power density of magnitude is 5 orders of magnitude higher than the sunlight. So this is extremely intense. So normally, if you don't take care about this in your Raman setup, you will use it to burn your samples instead of characterize it. And this is the first things that you have to consider when you start to study a material, because these are, for example, or some examples about what it happens when you don't control the intensity of the excitation light in your Raman setup. This is for CJS. Then if you increase the power intensity of your laser, you observe a shift of the main Raman mode. And this is due to the dilatation of the compounds because you are heating your sample. This used to be reversible. So normally if you switch off your laser, then you recover the temperature of your sample and then the normal spectrum of your sample. But also you will observe a broadening of your peak. Observe, like here is very broad, here is very narrow. And here you can see how increasing the power density, the fuel weight at a half maximum is increased a lot. This, at a given point, is due to a heating effect and also can be reversible. And finally, if you observe a change of the shape, the intensity or the appearance of a new peak is because you really start to modify your material. Because you are recrystallizing your material, you are decomposing your material, and you are obtaining new phases. And this is an irreversible damage. So this is the threshold that we don't or can't work with Raman spectroscopy. So normally this type of study is the first study you did in a material that you don't know how to respond to your Raman setup, or where you are using a new Raman setup in a very known material, in a really known material. This is an example of what happened with a very famous perovskites, and you know, yeah.
I have a question. What's the wavelength of your monochromatic laser that
You can use all that you want.
Yeah, but I mean
In this was using green excitation. In this case was using green excitation.
okay,
So
it's a green laser.
it's a green laser, but this is the case for all the kind of excitation. So you can use red laser, ultraviolet.
Heats of the sample, so I wanted to know the wavelength. And did you calculate the penetration depth inside the material? Because it's polycrystalline.
Yeah.
If it's polycrystalline, then the penetration depth will be much, and it will be given.
It's really densely packed. So normally green excitation in our absorber in copper indium diselenide or copper indium gallium diselenide, the penetration depth is around 100 nanometers, 150 nanometers maximum with green excitation.
Yeah, because the green is around 500 nanometers, or?
533 we're using, something like that, 32. So this penetrates around 100, 150 nanometer.
So you don't really have the full depth of your flash.
With this excitation, no. But you can change your excitation wavelength to infrared and have more penetration. And this is one of the advantages of Raman spectroscopy. I will show you later some examples where using different excitation wavelength, you can characterize all the layers in a solar cell without destroying it.
And it's a spot laser or a beam? Laser beam? Because this also comes.
Normally what we use here is a spot that is moving or the sample is moving. So you have the spot is around 1-2 microns, but you don't focus it in a single point. You move, you scan a large area, then you have some statistic and it's more representative of your sample. You can use in a single spot if you identify some special grain that you would like to know if it's a special secondary phase, and then it's very useful for that.
Yeah, because if you want to have an overview, you need to go in depth and also you need to go in.
Yeah, you can use macro Raman that is used really larger spot, but normally the signal drop a lot. So what we use is a small spot, but we scan this spot in a larger area. Then we have a very good statistic in 50 by 50 microns easily.
But one more question. So for how long did you put the laser that heats up this sample this much? Like you have this Raman shape from the
Yeah.
original position. So for how long?
Normally, Raman measurement take between few seconds to 2-3 minutes.
Yeah, but I mean, like for how long the laser was on the sample that it really makes this shift in the sample. Like for amorphous, if for a few minutes it can.
Yeah, absolutely. This spectra, normally we take every 1 minute one spectra, 3 spectra, and then we made the average of these 3. So in 1 minute is enough to have this kind of effect.
What's the influence of the power, laser power on the measurement accuracy? What the influence of the laser power on measurement, not on the material?
The measurement don't have any influence at all, unless you start to burn your optic. So you have to take care of your optic elements, because if you increase a lot the power of your laser, you can really destroy your optic components. But
It can only increase the intensity of the beat, because like if you did one accumulation, you will have 3,000 points. If you use 5 volts into 1 volt of laser, it will be like 12,000 points in the intensity line.
But in principle, in the measurement itself don't have a lot of effect, unless you are starting to hit, for example, your lenses, and then the curvature of your lens can change or be modified. And this is another example how power intensity can really modify a material. And these are the very famous perovskite, and you can see here how basically in this case we even destroy the perovskite, and it's irreversible. You are forming lead iodide here and not recovering anymore your material. So basically, with Raman spectroscopy, we take information about atomic vibration in a crystal, and is sensitive to crystal structure, composition, defects even. I will show you that we can even use to detect some type of defects, and stresses. And then the high interest in Raman is for non-destructive advanced assessment of the different layers in a solar cell device, because all of this is very relevant for the different layers we are using in a solar cell device. Once introduced some fundamental aspect of Raman scattering, why we use multi-wavelength Raman scattering, why we need to extend this to several different excitations, because this of course complicate the setups. This is, for example, this is the schema of the setup that we have developed at IREC for different laser excitation. Currently we have how many? 7, 8 excitation wavelength? so I don't remember, but we have for all the possibilities. This is the 6 or more. 8 different excitation wavelengths we have. So this is the Raman proof we developed in our lab. So we have one Raman proof for every excitation wavelength, and the thing is that you sometimes can combine even 2 different excitation wavelengths at the same time, or just changing this Raman proof, because everything is connected with glass fiber. You can really tune your excitation wavelength very easily. And this is one example what happens when we use in the same sample 2 different excitation wavelengths. With green excitation wavelength in a solar cell, in a SAGES solar cell, we are mainly observing cat sulfide and some smaller peak of SAGES. If we change the excitation wavelength to a red excitation wavelength, then CDS is transparent to this wavelength. So then we don't observe any more CDS, and what we observe is just the SAGES signal, just shifting or changing our excitation wavelength.
Why is it happening? Why changing the excitation band?
Because, for example, with the green, we can have access to characterize CDS. Okay?
Is it above the band gap?
It's above the band gap. So this light is very well absorbed by CDS. Okay, so it's mainly absorbed in the CDS, so only a few photons arrive to SAGES, so we observe a very small peak of SAGES. But this is, CDS is fully transparent to this excitation wavelength because it's below the band gap, so we can observe clearly SAGES without interference of the CDS. So using these different excitation wavelength, we can even switch to what we call resonant condition. And in this resonant condition, we can greatly increase the sensitivity to specific phases. This is, for example, kesterite, analyzed with green excitation, different etching times. We apply some etching at the surface here and so on, because we would like to see the effect of zinc sulfide as secondary phase on kesterite. With green laser, looks everything similar. Looks like we don't have zinc sulfide and nothing happens with the etching. Nevertheless, same samples analyzed with ultraviolet excitation change drastically. Why? Because the wavelength that we are using here is especially suited for resonant condition with zinc sulfide. Then, whoop, the zinc sulfide signal is really, really very big. Then we can detect, these are exactly the same samples. We can here detect zinc sulfide, and even the kesterite signal is very small. We are really enhancing the zinc sulfide signal. And we can observe how our etching process for zinc sulfide is very, very useful. So in 300 seconds, we have almost no zinc sulfide or very tiny quantities of zinc sulfide. Okay, this is the spectra of zinc sulfide that you have for comparison. Then it's very useful for optimizing processes. In this case, etching of secondary phases, but I have plenty of examples that you can use this. No. You etch 90 seconds, you measure. You can implement, but it's quite complicated, and this was just a proof of concept. We have implemented Raman in real cases, for example, for electrodeposition, and you can use it without problem. Even if you have a solution, if the medium is transparent to the excitation light, then you can use it. If you have colored medium, it starts to be more complicated. And the reason of this resonant Raman effect is because if you are exciting with a excitation wavelength with energies higher than your band gap, so normally you are exciting towards virtual levels. And then it has a low probability for inelastic scattering. Nevertheless, when you excite exactly with your band gap, then you increase a lot the probability of inelastic scattering, because you are exciting directly to a real state. And this is basically what you need for Raman, resonant Raman spectroscopy, to excite your sample with the excitation wavelength that is closer to the bandgap of your material. And these are very nice examples of zinc oxide with 2.8 electron volt excitation and with 3.8 electron volt excitation. So you can see that really the spectrum changed a lot because you are enhancing some of the modes that are really coupled to this excitation wavelength. And same for zinc sulfide using 2.4 electron volt or 3.8 electron volt, where you have, it's not only the difference, normally the intensity of this is 100 times higher than this. And the same here, you can acquire this very nice spectrum in few seconds. And maybe for this you need 3 minutes to acquire it. So normally in non-resonant condition you have a richer spectra, so you can have more access to the different vibration and so on, and a high sensibility for detection of small variation like doping, stress, texture. But in resonant condition you have an enhancement of single phase detection, is selective for the detection of the phase you want, and in strong sensitivity for bandgap changes. So if you would like to see the change of your bandgap because you are changing something in your process, then resonant conditions are much better. These are
the time is over.
okay.
But can we say we stop at 6 and not at 1?
No, I think that in 10-15 minutes I'm done.
Okay, good.
Because now there are examples, so basically this is a nice example for secondary phases detection once again. So basically in this system what we prove is we observe that in our kesteride we have zinc selenide, sorry, because this was the selenide kesteride. We have zinc selenide as a secondary phase. And what we observe is that introducing indium, basically this zinc selenide secondary phase disappear. And even if we have tiny quantities of zinc selenide, it was fully possible to detect it. For composition, then you have different possibilities. You can have one mode type Raman spectroscopy, and normally when the atomic distribution inside your crystal is very uniform, then if you change the composition, you have just one mode that shifts with the composition. So involve a random distribution of your atoms in your material and can be used, of course, for quantification of your composition, just based in the analysis of the frequency of your peak, on the position of your peak. But you can have two modes type. Then what happens, you have segregated distribution of the different atoms. Then you have two modes in your system. You introduce an additional mode. Or even you can introduce new peaks if you involve segregation of A atoms in one side, B atoms in another side, and mixed A to B atoms in another side. You can have new and unexpected peaks. And in that case, you can develop methodology based on the analysis on the frequency or even in the relative intensity of these peaks. And these are, well, I will jump this. These are nice examples of all of this. This is the zinc magnesium oxide case that has one mode behavior. So this means that when you start to replace zinc by magnesium, you keep the same. You don't introduce any additional peak. Basically what you observe is a shift of this peak, and following the shift of this peak, you can calibrate the composition of your layer by a very fast and single measurement. This is an example of two modes behavior, and zinc oxysulfide is always a very nice example. So you can move from pure zinc oxide material to pure zinc sulfide material, and then you observe how this zinc oxide mode start to shift, but then the zinc sulfide mode appear. and you have two modes behavior. Once again, following the ratio between the intensity of the zinc oxide mode to the zinc sulfide mode, you can have access to the composition of your layer. Here you can see how just following the Raman shift of the zinc oxide mode, you can have access to the composition, and here following the ratio between the intensity of the different peaks corresponding to zinc sulfide and zinc oxide, you can have also similar information. This is also useful, for example, for copper indium gallium diselenide. This is another example of two-mode system where you can have access to the sulfur and selenium composition just following the Raman spectrum. This is very relevant, for example, for graded bandgap concept, where you sulfurize selectively your surface, and it's extremely complex to analyze the composition. With Raman spectroscopy, you can quite easily know how many sulfur are you introducing in your surface, and it's extremely fast. And this is an example how just adjusting the sulfur content in your surface, you can maximize your efficiency. So you even can correlate the composition extracted by Raman with the efficiency of your devices. This is also useful for buffer layer, and you can have access to the thickness of your buffer layer using Raman spectroscopy. The same for the different thickness, just using the intensity of your peak, you can know the thickness of your buffer layer with Raman spectroscopy. And you can even correlate this thickness with the efficiency of your devices. And finally, much more complex but also possible is to assess the defect. For example, this is the typical selenium kesterite spectrum, Raman spectrum, and this peak corresponds to copper selenium vibration, this peak corresponds to zinc selenium vibration, and this to tin selenium vibration. So if you touch copper in your composition, or zinc or tin, you will see always modification here. And this corresponds, for example, to this kind of cluster of defects. Then you can have access to know if you increase it or not the quantity of some important defect for your material. You can see here how these peaks can be moved, just adjusting the composition of your material. So this is much more complex, but can be possible as well by Raman spectroscopy. Finally, applications in real life. This was a very nice application we developed that is for the zinc oxide doped with aluminum. Then we observed that the Raman fingerprint spectra is really modified a lot depending on the resistance of your layer. So we can have access to basically analyzing Raman and correlating with the electrical properties of the zinc oxide aluminum doped layer to the carrier concentration, and also this has correlation with the efficiency of the devices and the series resistance of your devices, because of course if this zinc oxide layer become very resistive, you will increase the series resistance of your device, and you will drop the efficiency of your devices. The same for other phases like OBC, but I will not go more in detail because it's quite similar. And this is the final example, how to, using all this excitation wavelength, you can have access to the full solar cell without destroying it. Using ultraviolet excitation, you can observe here the zinc oxide layer and characterize it. With the blue excitation and green excitation, you have access to cat sulfide perfectly. With this red excitation and infrared excitation, you can observe and you can characterize your absorber. All these spectra were taken in the same point, almost at the same time, just changing the excitation wavelength. And you have all in one. Of course, here you have photoluminescent disturbing a bit your Raman spectra, but we can work with this. And the conclusions. So Raman scattering is a powerful and non-destructive technique. And we can use resonant Raman strategies to increase the sensitivity, the detection, and to highlight and to identify some specific phases. And then we can provide also relevant structural, chemical, and morphological information of our layers. We proved this for different material, but can be almost used in all kind of material. We can also have access to know the thickness of our materials if are nanometric, and also selective detection of secondary phases. And we can even go further, correlating with optoelectronic properties of the devices. Introducing mapping, we can identify inhomogeneities in large area modules, even if I don't show any result here, but it's fully possible. And you can combine with PL and have a lot of information at the same time that we are working on that. So basically, this is all the materials that we have a lot of experience, buffer layer, all this, contacts, all this, absorber materials, all this, absorber interface, all this. So it's very useful for all them, and also for the control of processes and for the quality control in the industry. And finally, I would like to thank my group in IREC, all the funding program, Infinite Cell, and the Sensate ERC project, and a special thanks to the organizer and you for your attention. And I would like to dedicate this presentation to our Alex, because today is the birthday of Alex. So happy birthday, Alex. Enjoy your birthday. Thank you very much. And sorry if I was too fast.
Shall we keep the questions for later, or do you want to ask one or two sub-questions?
Please.
I have a question. In Tesseract, there is some people who take a ratio between different peaks to get the idea about order and disorder.
Yeah.
Do you believe that it's correct or not?
Yeah, I think that, yeah. But it's mainly the A1 peak. Then when you start to disorder, your material actually is a kind of evolution between, this is the kesterite phase, and then it's a kind of evolution between the kesterite to the estanite phase. So it's something in between. And then the estanite phase has a peak at lower frequencies than what you observe when you start to introduce this copper zinc disorder, because it's in between the evolution to these phases. You observe the shift of this peak and also to broaden of this peak, because you have a more disordered material. So I fully trust on this.
Yeah, I have a question. Have you tried to turn this Raman technique into a quantitative technique, meaning that you can analyze the amount of material or the amount of phases present or things like this?
The amount of phases is quite complicated. It is quantitative with composition, for example, but always you need some calibration samples. So you need another technique that helps you to know the composition of your sample, then you can correlate. You can quantitatively try to correlate, for example, in TCOs, your Raman signal with the carrier concentration of your layer, but of course you need whole measurement and so on that helps you to correlate. So Raman by itself is not a quantitative methodology. So in some cases it's possible.
When you say the doping level is from the asymmetry of the peak, or from the...
With the doping you introduce a new peak. So this peak, where is the zinc oxide? Is before, I guess. No, it's after one. It's here. It's here. This mode is related to defects introduced by the doping. So basically this is highly doped with aluminum, so highly conductive. This is less doped, less doped, less doped. So using the correlation between this and this peak, and because this is the doping and also correlate with the carrier concentration, so the ratio between these two peaks correlate quite well with the carrier concentration. It's because in this particular case we can use it. Maybe in another case it's useless or so deep. And yeah. But it's never quantitative by itself, Raman. You always need another technique that help you to transform it in quantitative.
Okay. Thank you, Edgardo.
Thank you very much.